Scale drawings and dilations. Little review on scale factor. We work with similarity and similar figures, and we grab two corresponding sides, and that makes a scale factor. It can be asked for in specific ways, though. I could say, what's the scale factor of triangle ABC to triangle DEF? And I can see that AB corresponds to DE. That would be 2 to 4. I can see that BC corresponds with EF, and that would be 4 to 8. I can also see that these outside two, AC and DF, correspond. AC is 3 and DF is 6. Notice that all these are 1/2. The scale factor then is 1/2. I could also write that as 1 to 2 with a colon. But I could request that scale factor the other way too, and it would be just as correct. It would be these exact same ratios, just turned around. 4 to 2, 8 to 4, and 6 to 3. Grab any two corresponding sides, make those ratios. That would be 2 to 1 or 2:1, as long as you put the corresponding sides in the correct order. You need to understand, though, a scale factor uses the same unit in the numerator and the denominator. When you use the same unit, you can actually use any unit you want. I could say 2 inches to 3 inches, and I could turn that into 2 feet to 3 feet, or 2 miles to 3 miles. All those would be true. But when you create a scale factor, make sure it's the same unit, and then you can use any unit you want. If you choose different units in the numerator and denominator, that can work too, but that's called scale, and we'll talk about that in a moment. You noticed in the previous example that I could pick any two corresponding sides and create a scale factor, and it would be the same thing. There's more going on than just that. As long as I choose two corresponding measurements of any type, I will get that same scale factor. Anything you can measure with a ruler. If we were talking about two similar quadrilaterals, yes, I could choose any two corresponding sides and get the same scale factor, but I could also choose any two corresponding diagonals. I could choose the two perimeters. As long as it's something I can measure with a ruler and its corresponding parts and the figures are similar, I will get that same scale factor. Now, it turns out if I have two similar figures and I make a scale factor, the ratio of the areas is the scale factor squared. Show you what I mean. Take a look at these two similar triangles. I've got a 3, 4, 5 and a 9, 12, 15. The scale factor of the small one to the big one would be 3 to 9, or I could make it 4 to 12, or I could make it 5 to 15. Notice in all three of these cases, it's just 1 to 3. Look at the perimeters. Those are corresponding things in similar figures. Notice that 12 over 36 is also 1 to 3. Now let's talk about area. To find the area, I take base times height divided by 2. Since we have a right angle, the base and height are the 3 and the 4, because there's a right angle between them, and the 9 and the 12. The area of the small triangle is 3 times 4 divided by 2, which is 12 divided by 2, or 6. The area of the large triangle is 9 times 12 divided by 2. 9 times 12 is 108, divided by 2 is 54. The ratio of the areas is equal to 6/54. Both 6 and 54 are divisible by 6. If I divide them both by 6, I get 1 and 9. The ratio of the areas is 1 to 9. The thing I want you to notice is if I take the scale factor, that's 1 to 3, and I square it, I'm going to square them both, or I can look at this as just 1/3 times 1/3, which is 1/9. If you square the scale factor in two similar figures, you get is the ratio of the areas. Once we know a scale factor, if we know the area of one of the shapes, we can find the area of the other shape. Here's an example. Let's say we know that these two triangles are similar. I can see the scale factor. The two corresponding sides are the 3 and the 12. 3/12 reduces to 1/4. Now, I know the ratio of the areas. I would square them both. 1 squared is 1. 4 squared is 16. 1 to 16. This triangle here would have 16 times the area if the scale factor was 1 to 4. I can look at this triangle and find the area like we did on the previous page. 3 times 4 divided by 2, 12 divided by 2 is 6. I know that the 1 corresponds with the small triangle and the 16 with the large triangle. I can make ratios now. 1 is to 16, that's the ratio of the areas. I know the area of the small is 6. That goes up top with this small number, the 1. 6/x, and then I can cross multiply and find what I need. 1 times x is x, 6 times 16, and 6 times 16 is 96. The area of the large triangle would have been 96. To create a scale factor, we need the units to be the same unit, and then we can use any unit we want once we've created that factor. But we can also use ratios and scale to find lengths too. Scale is when I'm comparing a small figure to a large figure and the units are different. A map is a great example of that. Take a look at this question. In planning a hiking trip, you examine the map of the trail you're going to hike. The scale on the map shows that 2 inches. Now, the units are different. I need to label the units. 2 inches corresponds to 3 miles in reality. If the trail on the map is 14 inches, the important thing when I use scale is that I put the same unit in the same position in the fraction. As long as you label your units and put the corresponding unit in the right spot, it will work. If the trail measures 14 inches, that's going to go up top with the 2 inches. My x below will be in miles, x miles. How long is the trail? And then we just cross multiply and solve. 2 times x, 2x, 3 times 14, which is 42. 2x equals 42, divide by 2, and x is 21. 21 miles. A blueprint is another example of how we can use scale to find lengths in a corresponding figure. When we use scale to create ratios, we label our units 3 centimeters over 17 meters equals 3 centimeters on the blueprint correspond with 17 meters on the actual object. EB, that's this length here, is 11.5 centimeters on the blueprint. These are similar shapes. 11.5. Make sure you put the units in the same position. The x then will be in meters. Just like we did on the last one, we'll cross multiply. 3 times x is 3x. And then 17 times 11.5. And then we'll divide by 3. Put that in the calculator. And here we're just going to round to the 10th. I got 65.16, which to the 10th would be 65.2. A dilation is another way we can create a similar figure using a scale factor. 1, it'll create a larger figure. It'll be an enlargement. If your scale factor is smaller than 1, it'll make it smaller. It will contract. It will be a reduction. To do a dilation, we need a center. It can be anywhere. It doesn't matter. And the process is measure the distance from the center to a point on your figure, and then take the scale factor, which I'm going to use a scale factor of 3 to 1. I just chose that. It will depend on what you're doing. And all I do is multiply that length by, in this case, 3. 3 times 20 is 60. And I go that distance from the center of the dilation to my new point. If this is point A, we sometimes call this point A prime, meaning the new location for A. Repeat the process for your other points. Take the distance from the center to a point on your figure, measure the length, I measured 40 millimeters, and multiply that by your scale factor, which was 3 to 1, 3. 3 times 40 is 120, and I measured from the center to my new point a distance of 120 millimeters. If this point on the figure was called B, this would be the new location for B, or B prime. Has nothing to do with prime numbers. That just means new location for B. I completed the measurement for my last point, which I'll call C. My new location then is C prime. I measured 15 millimeters and went from the center out to my new point, a distance of 45 millimeters. And then I'll connect those 3 points. Take a look at the 2 triangles. If I've been accurate, every side on the new shape will be 3 times larger exactly. And the area, remember what we said, if you have a scale factor of 3 to 1, the ratio of the areas is the scale factor squared. That would be 9 to 1. The area of this bigger triangle would be 9 times bigger. A dilation is an example of a transformation. Some other transformations are rotation, reflection, translation. Don't confuse translation with transformation. And we'll talk about those in chapter 12. What I want you to know, though, is the original shape in a transformation is called the pre-image, meaning before, and the new shape is called the image, or the result of the transformation. That last example may have seemed a bit confusing, but it turns out that actually on the coordinate plane, the one we graph on, it's very, very simple to do a dilation as long as you use the origin for the center of your dilation. All you do is take each point and multiply by the scale factor and draw your shape. Here's what I mean. A is the point x is negative 6 and y is negative 10. B is the point x is negative 10, y is negative 6. C is the point negative 4 for x and negative 4 for y. A will go to the new location for A. We'll call that A prime. Multiply both of these by 1/2. That's negative 3, negative 5. Multiplying by half is the same as dividing by 2. B will go to B prime. Multiply by half. You get -5, -3. And C will go to C prime, the new location for C, multiply by half, -2, -2. Plot those 3 points, connect them, and you're done. The rest of this video is questions from your assignment. In question 1, we have 2 pools, and they give us the letters that describe them, and they label the dimensions. What is the scale factor? Now they ask for it PQRS to WXYZ. We need 2 things that correspond. It can be any 2. WX, that's the first 2 here, corresponds with PQ. That's the first 2 there. So PQ and WX. Now, they asked for the PQRS first. So we need to put that one first. Our scale factor then is 24 over 16. We'll divide both those by 8, and we get 3 to 2. Note that they ask for the answer as a reduced fraction, 3 to 2. Here we have 2 similar triangles. They told us the order. They've stated it correctly for us. And we want the scale factor of ABC, that's going to be first, then, to triangle FGH. We need 2 sides that correspond. AB, that's the first 2, would correspond with FG. Well, they don't give us FG, so that one's not useful. AC, that's the outside 2, would correspond with FH. AC with FH. There it is. That's going to be 12 to 15. We put triangle ABC first, so AC goes first. We're going to reduce that, reduce fraction, divide both by 3, and we get 4 to 5. In question 3, we have 2 similar quadrilaterals, and they tell us the scale factor is 2 to 7. That's ABCD to WXYZ, 2 to 7. The 2 corresponds with the first one, the way they've stated it. They've asked us to find XY. XY, those middle 2 points would correspond with BC, the middle 2 points. They give us BC, so we're ready to go. 2 over 7 is our scale factor. 2 corresponds with quadrilateral ABCD because they stated it first. And the 7 corresponds with WXYZ. Since we want to find XY, and XY is the middle 2, we're going to use BC. BC is 21, the middle 2. And X will be the length of XY because those are corresponding segments in the 2 quadrilaterals. Cross multiply, 2x equals 7 times 21, and divide by 2, we get 73.5. Question 4 is like the example in the teaching, and I think we're finding the same length even. We're going to find EB on the actual shape. The scale is 2 to 15. That's centimeters and meters. And remember, when I use different units, I need to make sure I put the corresponding unit in the same spot. So the 16 centimeters goes here, and my X, which is the length of the actual wall, will be in meters, just like the 15. Cross multiply, 2x equals 15 times 16, and divide by 2, and x is 120 meters. Question 7 is just like the one in the teaching again. 2 inches represents 3 miles. The trail is 6 inches. Inches go in the same spot. Put our x below. It will be in miles and cross multiply. 2x equals 3 times 6. 2x equals 18. Divide by 2, and x is 9. 9 miles. In question 10, it's a lot like the last one. They just given the information a different way. We have a model and we have a scale. His actual home is 40 feet wide. Would go right here. And the actual height is 37.5, 37 and 1/2. I know then that 40 feet over 8 inches equals 37.5 feet over h inches. That's what I'm trying to find. And just cross multiply again. 40 times h, 40h, 8 times 37.5, and divide by 40. And the calculator says 7.5, and that would be inches. In question 50, the scale is 1 to 50. Notice they don't give a unit. This is an actual scale factor. I know the model, it's going to correspond with the 1, is 2 feet long. I can put my x below and solve. Now notice something here. It's x times 1 equals 2 times 50. In other words, all I did was take the 2 times 50. So I can just take 3 times 50 and 1 times 50 and I'm done. So the length would be 100, 2 times 50. Multiply by 50. 3 times 50 is 150. Multiply by 50. 1 times 50 is 50. Question 14 is just like the last example. We have a 56 to 1 scale. They don't give a unit. It's the actual scale factor. The drawing is going to correspond with the 1, and the actual house will be 56 times bigger. You could turn these into decimals if you want. That probably makes it easier. 5/8, 5 divided by 8 is 0.625. 1.625 inches by 1.5 inches. Now all I really need to do is multiply by 56, but understand again, you're really solving a ratio. 56 over 1 equals, the 1 corresponds with the drawing. Take one of these lengths and put it below 1.625 and your x above, and then notice again, x times 1, x equals 56 times 1.625. All I do, because it's 1 to 56, I can just multiply by 56, and I got it. X ends up being 91. Now the issue is, this 1.625 was in inches, so this is 91 inches. If I want to turn that into feet, I'm going to divide it by 12. 91 divided by 12 would be 7 point, it says to the nearest hundredth, 7.58. Now I need to do that with the other one. Take 1.5, multiply it by 56, just like we did here. 1.5 times 56 is 84, but that's going to be inches, and it's asking for it in feet. Take 84 and divide it by 12, 12 inches in a foot, and you get 7. So we have 7.58 feet, that's to the hundredth. This ended up being exactly 7. So the actual dimensions are 7.58 by 7, and then we're going to find the area. Area is base times height. We'll just multiply these two. 7 times 7.58 is 53.06. One thing I want to mention is it's always better to use an unrounded answer to find another answer. Now I use in this question 7.58 to find the area. It would have been better if I'd used this before it was rounded. That's 91 over 12. But in this question, I allowed it either way. You can either use the exact or the two rounded answers if they both have to be rounded to find this answer. In question 15, they give you an actual scale factor with no units. That means I can use any unit I want. What I know is that I have a photo and that in reality, everything is 10,700 times bigger. What I'll do then is take this 2 and multiply it by 10,700, which is 21,400. 2 inches in the photo would represent 21,400 inches in reality. 2 centimeters in the photo would represent 21,400 centimeters in reality. And 2 millimeters would represent 21,400 millimeters in reality. I can use any unit I want. The issue is they want it in feet here, kilometers here, and meters here. I need to use these conversions then. Here I'll divide by 12. I'll take this number, because that's in inches, if I'm using inches, and divide it by 12. We're going to round that to the nearest tenth. 1,783.3. 2 centimeters is this many centimeters in reality. And I know that 1 kilometer is 100,000 centimeters, so that's in centimeters. I'll divide it by 100,000 to make it kilometers. I get 0.2, 0.214, 0.2. And the last one, I'll take the 21,400 because that would be in millimeters if I want it to be. And I'll divide it by 1,000 millimeters to make it into meters. And that is 21.4. Question 16 uses the idea that if we have a scale factor, we can square that to get the ratio of the areas. They give us the similarity statement, and we can see that AB, the first two, corresponds with EF, the first two. That's 38 corresponds with 48. Both of those are divisible by 2. That's 19 over 24. And then ABC, that's 38 to 48, reduces to 19 over 24 is 19 over 24. The scale factor for the second one, because we're going to put EFGH as the first one, that's 48 to 38, which is 24 over 19. We're just going to flip that, 24 over 19. Write these as reduced fractions. What is the perimeter? We know the scale factor is 19 to 24, and we know the perimeter of the small one is 114. 114. A scale factor is any two corresponding lengths that you can measure with a ruler. Could be the diagonals here, it could be any corresponding sides, it could be the perimeters, and that's what we're using. We know the perimeters would be in that same ratio, they'd make the same scale factor. Cross multiply and solve, 19x equals 24 times 114, and divide by 19. And we get 144 So the perimeter is 144 of the bigger shape. To find the ratio of the areas, we take that scale factor and square it. 19 squared is 361. 24 squared is 576. And we use that. 361 over 576. We know the area of the smaller one is 722. Cross multiply and solve. 361x equals 576 times 722. And divide by 361. Run out of room here. And we get x is 1,152. The area is 1,152, and that would be feet squared. In question 18, we have a dilation centered at the origin with a scale factor of what? Well, the question is, what do we do to 8 to make it 2? 8 times something, we'll call it x, equals 2. I'll divide that by 8, and x is 2 over 8. Divide both by 2, and you get 1/4. In other words, if I take 8 times a fourth, I get 2. You're dividing it by 4. 24 times a fourth, I get 6. The scale factor is 1/4. And when I multiply by a number less than 1, it contracts, it gets smaller. And when I multiply by a number more than 1, it gets bigger, it enlarges. Since this makes each point smaller, it'll make a shape smaller, and it is a reduction. For question 23, remember back to the teaching when I did a dilation with a scale factor of 3 over 1, and what I said was that every length would be 3 times bigger. In this case, that's a weird number, every length would be 8/7 times bigger. Just take the segment CA, that's 14, multiply it by the scale factor, 8/7. These will cancel because 14 is over 1. Divide by 7, you get 1. Divide by 7, you get 2. And 2 times 8 is 16. That's C prime A prime. That's the new CA, segment CA, is 16 in length. Question 25 is another quick one. They give us 2 corresponding lengths, and it's a dilation, and they want the scale factor. Now, they didn't specify it a certain way, so we could actually do it either way here. We could say 10 over 8, divide those by 2, and that would be 5 over 4. That would be acceptable. Or you could say 8 over 10 and divide those both by 2 and say 4 over 5. So either one of these two will work in the answer box. Question 26 is another quick one. This is like the example where I drew the shape and it was a scale factor of 1/2. As long as it's centered on the origin, it's just as simple as multiplying by your scale factor. Take each of these points times 1/2, which means you're going to divide them by 2. A prime would be -6/6 times 1/2, divided by 2, and you get A prime is -3/3. B prime, multiply it by 1/2 or divide it by 2, and you get -1/1. And C prime then is -2/2. Question 27 is a dilation, but the center isn't the origin. This is a little bit trickier. Remember how I took a ruler and I connected the center of the dilation, which is the black dot, with a point? Now take that length, and since the scale factor is 2, double it. That means we're going to go left 1 up 2, left 1 up 2, left 1 up 2. And the new location for A prime, will be right there. This is the original length from the center, and this is the new length from the center, twice as long. You can do this just by counting the rise and the run, and remember the scale factors too. You're just going to repeat it one more time to make it twice as long. Let's do point C now. From the center, I go left 1 and up 1, 2, 3, 4. Repeat that one more time to make that distance twice as long. Left 1, up 1, 2, 3, 4. And this is the new location for C. First one was A prime, and this is C prime. This here is the length we're talking about. This was the original length, and this length was twice as long. Repeat the process with point B. Notice from the center of my dilation, I go left 2 and up 1 to get to B. It's going to be a scale factor 2, so my new segment, that's this one right here, is going to be twice as long. I'll go left 2 and up 1, and there's my new location for B. That's B prime. This is the segment we're talking about. From the center to the point, I doubled it to get this length here to make a scale factor 2. Scale factor is also sometimes called magnitude when you're doing a dilation. Now what I'm going to do is connect my 3 points, A prime, B prime, and C prime. And that triangle is the answer. That triangle, each side would be twice as long, and the scale factor is 2 to 1. The area would be 4 times bigger. In question 29, we're back to the center being at the origin, which makes it a whole lot easier. The scale factor is 2. Take those points, A, which is 2, 3, multiply the points by 2. As long as the center's at the origin, that's all we do. It's got to be at the origin to do that. That becomes A prime, which is 4, 6. B, which is the point negative 2, 2. Scale factor is 2. Multiply it by 2, and you get negative 4, 4. And C, the point is negative 1, negative 2. Scale factor is 2. That becomes C prime, which is negative 2, negative 4. Plot those 3 points. Connect them, and you finish the dilation. This is really the same as the last question. It's just they didn't give you a figure to use. They gave you the points. But the scale factor is 2 again. That means we're going to take the original points and double them to draw the image. Remember the original shape's called the pre-image. A prime, double A, it will be 4, 4. B prime multiplied by 2 will be negative 4, 2. And C prime will be negative 2, negative 2. All we're doing in question 34 is drawing the image, and that is the image.